there are two main streams in study and application of deep neural networks. They differ in the approach that the initialization of the neuron weights in hidden layers can be combined in different ways. For example, one of the methods is that the neural network is very sensitive to the triggering of hidden layers, especially if the number of the hidden layers increases or is greater than 3. One of the masterminds in deep learning, Professor Hinton, was the first to try and solve this problem. The idea behind this approach was to initiate the weights of the neurons in hidden layers with the weights obtained during unsupervised training of an auto-associative neural network. An auto-associative neural network would be nothing more than a stacked restricted Boltzmann machine, which is a stochastic Euler-Lagrange dynamics, giving us the Brownian motion, the state of that Brownian motion, in this case being the plotting of fetch data, get data for Mesos. But in this course, we're going to focus on the backpropagation of the stacked SRBM, the stacked auto encoder trained with large array of unlabeled data. And there's another approach pioneered by Joshua Bengio, created specifically for methods of initializing hidden neurons with specific functions of activations, methods of stability, and training. And the success of this is a rather connected one. And we want to be able to capture a specific hysteresis or a specific moment of kurtosis and create a norm difference between peaks, between different sections of the tailedness exhibited by the distribution. And for this, we need a simple moving average, a binary search prototype that is probably linear. We want to be able to make this sublinear, but if not, it's very easy to become that an algorithm that is able to smooth a set of parameters becomes quadratic in nature, because you're almost dealing with at most 2 instances of that. Now, the beauty of this is that we can get a smoothing function based on the average, the cumulative average of autocorrelation functions. Autocorrelation functions are, again, the divergence and convergence of values from one moving average, meaning a simple moving average, meaning that historical norm that pulls all values towards it. And a lot like stock prices, requests, bandwidth, throughput, all seems to be mean reverting. Mean reverting being returning to its norm. Of course, we're very creative in this sense because we're utilizing what we've understood as coarseness and granularity, being the standard deviation of 2 local points in a manifold, a Poisson manifold, if you want to get fancy. But we're talking specifically here about a restricted Boltzmann machine, a neural network with multiple hidden layers. Now, the layer-wise training of this is an unsupervised training. The fine-tuning of the neural network requires supervision of some sort. The dividing stages of this training with parameters gives us an opportunity to use data of different volume, not specifically structure. And as I said before we go into the activation function, we need to reduce the complexity of the data. And for that, we use principal component analysis methods that are readily available on Bioconductor, which is a fascinating library on R that you can use from genomics, but you can also use specific utilities such as this PCA method. Now, this is mostly pertaining to the idea that you can pre-process, you can pre-train with the NLPCA, with a PCA, with a probabilistic component analysis, with single value decomposition. You can make the data not left or right skewed, but actually just much more balanced. And it takes less time to train because data has been normalized in this sense. So it might seem a little bit schizophrenic at the beginning. We were multiplying raw values with digital filters in order for us to attenuate so we could see those curves. But now we need to reduce the dimensionality. We need to make sure that we are abiding to a more rational sense of what the raw norm towards the origin, meaning the distance from the centroid of local importance in this case. And what's very curious about the neural network is that you can find the outputs and the inputs. You can actually find and transform, use the outputs as your inputs using the inverse nonlinear PCA. And then we just graph it. And you can see that we can single out which of these momentum classifiers is too skewed to one side. So it might actually not be giving us the local or global outliers. And this is why we're graphing them. So we can see the cluster itself become less skewed. And if it doesn't become less skewed, then that digital filter needs to be replaced. The only way to do this is by graphing the principal component analysis of the training data. You can do this several times until you find the variation and covariance that you desire that would make feeding the neural network a more pedestrian-friendly method of teaching.